Here's an example of a typical bomb calorimeter problem. You're going to see the problem written on the screen right in front of you, and I've just done a summary of it on the board. Bomb calorimeter is something we're going to talk more about in class, but it is a way to find the heat evolved from a reaction. Typically for bomb calorimeters, that's a combustion reaction. So in this case it's methane. I wrote out the combustion reaction. I didn't balance it. You can, but you don't need to. You can balance it if you want to. You don't need to do so for this problem. We know there's a 7.3 degree temperature increase. We know the heat capacity of the calorimeter. And we want to know the energy per gram. We're also given the mass of the CH4. How do you solve this? Well, actually all of the calorimeter problems are solved in a pretty similar way. At least the start is the same, where you go the sum of the Q's equals 0. The law of conservation of Q's that we're going to deal with. The first one is called the Q of reaction. Because we know that energy is coming off of this reaction, there's a Q for it. And that's actually what we're looking for. The second part is the Q of the calorimeter. So every bomb calorimeter will have this identical setup or something pretty similar to it. And again, you're solving for a Q of reaction. So there's a 0 on one side, so it's pretty simple to say Q of reaction equals negative Q cal. Well, Q cal, remember that's MCP delta T, or MCP is the same as C. And for a bomb calorimeter, you're usually going to use... Then what do you do? Well, we know all these numbers. C is given. It's 11.3 kilojoules per degree Celsius. T is also given. It's 7.3. Do we care if this is in degrees Celsius or Kelvin? No, because the temperature difference would give the same number. So whether this is Celsius or Kelvin, it actually wouldn't matter. Both would cause this to cancel, actually. Okay, now let's see what I get that for that. It's minus 83 kilojoules. So if you calculate that all out, minus 83 kilojoules, you'll see the degrees Celsius drop out. Now, is that my answer? Not exactly. This is true for 1 mole of this, 1 mole of the methane. However, I don't have 1 mole of methane in my question. I have 1.50 grams. So what am I going to do? I'm going to do something that might look a little strange at first, but this is a normal next step in a bomb calorimeter problem. Per gram is equal to minus 83 kilojoules, and then I divide that by the mass, 1.50 grams. That's the mass given of the methane, so that's how much is reaction to cause this kind of energy, and you're going to get minus 55 kilojoules per gram. That's your answer. Okay? So there's these two typical steps when you do this kind of problem. The first step is here, when you're solving a bomb calorimeter problem. And remember, this first part is the same for any calorimeter, but the bomb calorimeter will always look something like this, and you're going to get an energy. Then typically, it's going to ask you for the energy per gram, per kilogram, per mole, something like that. You're going to have to divide by whatever number they give you here to get your final answer.